Further maximizing farm production in a sustainable way has widespread benefits for us all, and fortunately, there is a positive path forward. Welcome to Redox Grows. I'm Jim Morris with Redox Bionutrients. This is the latest in our series of technical podcasts where we take a deeper dive into the science of successful farming. And I'm absolutely thrilled to be able to visit today, all the way from France, with Dr. Olivier Husson. Olivier, thank you for your time.
Yes, thank you for the invitation.
Olivier is a system agronomist and agroecologist with 30 years and more than 120 publications. He is a world authority on what we're going to be talking about today. When I first arrived at Redox about 3 years ago, his name came up, and it continues to come up because he is revered throughout the world for his areas of study. And Olivier, you spent a lot of time in pretty interesting places. As part of your research, you were in Vietnam and Madagascar. Tell me more about that.
I'm an agronomist specialized in tropical agriculture. I like the idea because things are going faster. It's easier to understand the processes there. I work mainly with farmers, small-scale farmers, trying to develop some cropping system that 30 years ago it was not called conservation agriculture or agroecology or regenerative agriculture, but it was the foundation of these approaches. I work mainly with rice-based cropping systems. So rice can be grown either in irrigated, the fashion that most people know, but it can be grown also like wheat in aerobic conditions. So that's what makes a very interesting thing is that I started in the plain of reeds in the Mekong Delta in Vietnam with irrigated rice on very specific soil that when they get oxidized, when they dry out, they acidify tremendously. pH can go below 3. And at that time, I started to work on this redox and pH balance. And the redox chemistry in paddy field is very well known since the 70s. Later on, when I worked on aerobic rice in the mountains in the northern of Vietnam or in Madagascar, we were developing the cover crops, many aspects of this, the no-till and all these things. And I wonder myself why redox potential is so important in paddy fields, but we never talk about this in aerobic condition. And it's then that I started to work on trying to understand how important it was in this the cropping condition that we meet in most of the agriculture in the world.
That's a good area to emphasize, even though you've had experience in rice. This application that we're talking about today works for all crops, correct?
Yes. Rice is nice for this because it can grow underwater in very reduced condition or in aerobic, so it can grow in the full range. Most of the crops cannot grow with the roots in the water.
Rice is a fascinating crop. I spent 14 years in the California rice industry, and I have a lot of fond memories from that. And I'm glad it aided your research. So I think it would be good to start with some of the definitions of what we're discussing today. I admit I am not a scientist. I'm a student. I imagine a lot of the people that are going to be following along with this will be in the same way. They want to know more, but they need some assistance and to kind of work their way through it. So can you talk about redox potential, pH, those aspects, and how it's important for healthy fields and productive fields?
So it's most of the chemistry and the biology is based on two main kind of reaction, the exchange of proton and the exchange of electron. So we need to measure the availability of proton. This is what we do with pH. So pH is characterize the availability of this H plus, the proton with a positive charge. When redox potential that we name EH characterize the availability of the electrons with a negative charge. And according to the amounts or to the availability of the proton and the electron, it will change many things. It will change, for instance, the form of the mineral nutrients. So it will make them soluble or not soluble. It will, in biology, it will change the activity of an enzyme or the ability of a signal to enter the core and starting making proteins. So it's actually we don't know in physiology at that stage. Now we are at the level where we don't know what is not regulated by EH and pH. So it's really at the core of the functioning of the living, and it's the energy behind this. Having a lot of proton and electrons, you will have gradients, electrical gradients, and you will be able to use this energy. So when you have more energy, you can do more things. So you will have plants that will grow better. You will have soil that will sustain their capacity to be well structured. You will support the aggregation process. You will solubilize some nutrients. So many things are related to this that it's difficult to see things differently for me now. I just look everything with this background.
Balance is what is needed for optimum production. Of course, there's nuances within there.
Yes, you need gradients to use the energy, but you need a balance. If you have too much or too less, it will not work. It's like a carburetor for an engine. If you have only fuel and no oxygen, it will not work. If you have only oxygen and not enough fuel, it will not work. So it's a balance. You really need to have a balance, an equilibrium. And this is very dynamic and changing. So one very important thing is how you can sustain this balance.
And this is not only a scientific principle, but we can actually measure it. Our company, for example, is working with Sensine based out of France. I believe you know that company. There are many that are doing this, and there are scanners that rapidly detect pH and EH in plants as well as other key nutrients. It's important to have, as we discuss this, farm applicability, right? It's one thing to have a scientific principle, but we want to make sure it works in the field, correct?
Yeah. The main difficulty was that the classical methods to measure pH, but especially EH, are extremely long, difficult, time-consuming, delicate. It's a real nightmare. In fact, it took me more than 5 years to be able to measure it properly in soil, and 2 more years in plants. So, and it was in no way something that you could use at farm level to steer your system or get information how your field are working. And that's why we've been working with Sensing to develop tools that can make the measurement very easily in 10 seconds. You have your measurement. With electrochemical methods, you needed a lot of experience. You were never really sure of your results, and it would take 10 to 15 minutes to have one measurement. So it was really, even for research, it was really complicated. Now with this new device developed with Sensing, for it's calibrated for a few crops, you can make measurements, and we are learning a lot in the past 2 years. Since we have these tools, we can measure a lot and understand a lot what's happening.
And that's really exciting, right? I mean, you've been at this for decades, and to see it come this far must be very rewarding for you.
Yeah, sure. You would have told me 5 years ago that we would be able to do this at that stage, to have understood all what we did in the past 2 years. I would say no way. But now we made a lot of progress, and it's really thrilling to see that we are really on the right tracks, because we see more and more things. So I can receive data from a cornfield or from grapevine fields that I've never seen. I received the data and I said, this treatment works better than this one has this problem, and the farmer say, yes. How can I do that? So it's we have a lot of fun.
Oh, and just imagine where we'll be 5, 10, 15 years from now as well. It's fantastic frontier being opened up here. So farmers have a lot on their minds. They are ultimate risk takers. How important do you feel they should prioritize redox potential?
It's really a very good way to look at things. It provides a lot of information. Sometimes you have results you don't understand, or result in research that seems contradictory. It's just because if you are not on the same EH and pH condition, things can work completely differently. As I said, an enzyme, for instance, will be effective, will be functional mainly in reduced conditions when there's enough energy. And when there's not enough energy, it will be fault and not efficient. It cannot work. So you can measure things, you think they are there, but sometimes they are, according to EH and pH condition, they are functional or not. You can have the same for the nutrients. You measure, you have a lot of iron in your soil, but according to EH or pH condition, this iron can be soluble, so the plant can access it, or the iron will be not soluble. And just because you are in more oxidized and alkaline condition, then reduced iron is needed for absorption. And you have the same thing for manganese, for many. So it really regulates so many things that if you don't know where you are, and if you don't know what your practices are doing, you can never find the right place, because there's this balance that we were talking about. We need to try to stay as much as possible in this balanced environment. If you don't know where you are, and if you don't know what your practice are doing and where they bring you, there's almost no way you can be at the right position.
I'm concerned there may be quite a few growers that are in that state as we speak, but I believe that in the future that will change significantly for the positive. I'd like to ask you about photosynthesis. The sun is a key element working in conjunction with the plants. I've heard farmers described as actually solar engineers to some degree, harnessing that sunlight through the plant in the form of photosynthesis. Sometimes people look at the key to healthy plants being healthy soil, but I believe you have a different view, that it all starts with the plant, that is the foundation of everything. Can you describe that?
Yeah, so first the photosynthesis, it works like a solar panel. It takes the energy of the photons and create gradients of electrons and protons. It's what you have in the chloroplast. So you transform this energy of the photon into electric energy, and then you store this, you change the form of energy to store it. You will store it in chemical bonds in the sugar made during the photosynthesis. So basically you store this electrical energy into carbon hydrogen bonds, mainly, also carbon bonds. So the photosynthesis is just like a solar panel, transforming the energy of photon into electrical energy, and then storing this electrical energy, changing it into chemical energy. And then the energetic functioning of any living cells in the mitochondria just does the opposite, takes back this energy in the chemical bonds and transform it into electrical energy that will then again will provide the key, the smallest ton of energy in the cell, the smallest unit that the cell will use. Because if you have too much energy, the cell cannot use it. You need to have to use it by small step. It's like having a high voltage. You don't plug your computer on the high voltage line, so you need this smaller bond. But the mitochondria does this basically. And then, but do we need a healthy soil to have a healthy plant, or is it the opposite? It's both, but there's something sure, is that we know how to grow plants without soil. We can have silicon balls and irrigated with nutrients, and you will grow plants with no soil. But if you remove this plant from the soil, very rapidly you get sand and stones. There's nothing left. So all the energy of the system comes from the photosynthesis. So you need energy to make aggregation, to feed the microbes, to feed the fauna that will make the galleries and improve the soil structure. You need energy to feed the bacteria that will provide antibiotics to protect your plants. You will need energy to feed the mycorrhizae that will collect phosphorus and water for the plant. So all the energy of the system come from the photosynthesis. Okay.
And the soil is indeed important. And can you talk a little bit about that, the biological activity, the organic matter? There's been a loss of carbon in the soil as well in intensively farmed areas. So how important is good soil to the process, including carbon?
So first, to have good soil without carbon, it's difficult. I don't know how to do this. A good soil structure is the key of many things. It will provide habitats with EH and pH conditions that will be very different in space, so you can harbor very different microorganisms that will do different things. A bacteria that fix nitrogen needs to be in very reduced conditions. A bacteria that will transform to nitrate for the plants will need a lot of oxygen, will be in oxidized conditions. So you need to have these different habitats for the microorganism, otherwise your nutrient cycle will not work well, your different function will not work. So we need this good soil structure. And to have good soil structure, you need carbon, you need biological activity to move things, to glue things, to sustain the aggregates. The stability is important. And once you have this, it's always chicken and eggs, in fact. When you have a good structure, you can have better microbiota, better microbes for what you want to do. And at the same time, these better microbes will sustain a better soil structure. So that's the key. And carbon in all this, it provides two things. I'm always not really comfortable when we talk about carbon. We need really to make the distinction between two or at least two different forms of carbon, or three forms, let's say. You have carbon like glucose, like lipids, that basically is there to provide energy. It's the battery that will have all these carbon hydrogen links that you will use to get back in energy for the functioning of the metabolism, of the growth, of the health of the plant. So this is the liquid carbon. This is the carbon that brings the energy. Okay, and then you have the carbon that is there for the structure. It's the humus, humic acid, fulvic acid. Basically, from glucose to humic acid, you just use the H2 from the glucose is several types, one carbon, two hydrogen, and one oxygen. So with humus, what you basically do is that you condense your carbon. You use the H2, you use the energy in the CH and OH and bonds, and you get chains of carbon, really condensed carbon with less energy, but that will be there for the structure. Okay, and if you are in strongly oxidized condition, you don't condense your carbon, you just burn it and you get CO2. CO2 is the form of carbon that you took all the energy you could take from the glucose or from the lipids, and then you burn it, and CO2, there's no more energy you can use in it. Okay, so we really need to have these two different aspects of carbons. The one for the energy that will feed the microorganism, and the one for the structure that will be there for the soil structure, for building the house. You need bricks, and you need people you need workers to build the house and to paint it. That's the microorganism and the fauna. So you need to feed them with the energy.
That's fascinating, and thank you for the analogies. They're very helpful for the non-scientists. I have a question for you on farmers. So they are sophisticated, they are very good at what they do, but there are times when they may apply too many of the macronutrients, your NPK. I've heard it stated sometimes that nitrogen can be applied a little heavier to kind of ensure that there's good production. How does that affect the overall balance in a field?
So we have to make the difference between different kind of nutrients. You will have and the form in the which you bring them. You will have nutrients like potassium, K plus. If you bring with KCl, you bring a chloride that is oxidizing at the same time. But basically, having an excess of potassium, you have this plus charge that you need to absorb this. The plant needs to mobilize pumps, and if you have too much of potassium, for instance, you will reduce the absorption of other positive charge, like calcium or other. The second point is for nitrogen. Nitrogen is very specific because the plant can absorb nitrogen under various forms. It can be organic, but in our system, most of the time, it's far too much under mineral form. So it can be nitrates, which is the oxidized form of nitrogen with a negative charge. Or it can be ammonium, NH4+, which is the reduced form of nitrogen with a negative charge. And this creates very complicated things. When a plant absorbs ammonium, so NH4+, it absorbs positive charge and a lot of protons, so it will acidify a lot, and it will expel from in the roots some H+, so it will acidify strongly in the rhizosphere, in the root zone. Okay. At the opposite, if the plant absorbs nitrate, it will get oxidized a lot. It will take a lot of energy to transform these nitrates into ammonium before reducing again to amino acids. And it will alkalinize a lot the plant. So it will create an imbalance in pH and a lot of oxidation. And so excess, you need nitrogen for the photosynthesis. It's one of the key elements. But if you bring it in excess, or more important, if you bring it in unbalanced form, you will get an imbalance in the plant, and that will make it really loss of energy, and it will be sensitive to disease, and the growth will be reduced because it will spend energy to transform, to reduce this oxidized form into more reduced compounds like amino acids. So it's a waste of energy, and there's a snowball effect. The more the plant spends energy to correct the form of nutrients you bring, or to correct the condition in the soil so that it can absorb the nutrients, the less energy it has to produce leaves, so the less energy it will capture, and it's a vicious circle like this.
So too much is not a good thing. Is less potentially more, or at least ideal amount, solubility, things of that nature? If a grower has that expert information coming in that is based on the science, can less be more and ultimately be a better product in the end?
Yes, but and it's also a lower cost.
Yes, there you go too. That's important.
Yeah, there's many things. So the form of nutrient you will bring has a tremendous impact, but also the form for micronutrients, especially like manganese, iron, that are key macronutrients for photosynthesis. So if you don't have enough in the plant, photosynthesis is not working well, the growth is not working well, there's not enough energy in the system, and you go down. These elements, iron, you often have iron in the soil. I don't know many iron deficient soil in the world. It's really extremely rare. The problem is that most of the time in aerobic growing conditions, when there's not enough energy in the soil, when redox is not low enough and pH is not low enough, iron will be in the form of oxide or hydroxide, which is not soluble. So although there's plenty of iron in the soil or plenty of manganese in the soil, it's the same process. The plant cannot access it directly. Okay, so the plant will have to spend a lot of energy to reduce, so release electron, release proton, acidify, so that the iron will be under a soluble form that can be absorbed by the plant, and all this energy is lost again.
That's not good. Pests and disease, how much more of a threat are they if you don't have a balanced environment?
So that's the one of the most fascinating part. We've been able to identify each living organism has some specific redox and pH condition in the way under which it will develop well. Okay, and once it's able to develop, it will try to bring the environment to this level. So that's the strength of microorganisms. They are very strongly influenced by EH and pH condition, but in the other way, when they develop, they have very high capacity to bring the environment to their optimal level. And the plant will use this a lot. They will use the microorganism to change, to alter the EH pH condition to the favorable level. That's why they feed them. A plant releases on average 30% of its photosynthetic product into the soil. Mainly it's to feed this microorganism that will regulate the environment. What we've been able to show is that the different pathogens are adapted to different conditions. For instance, the soil fungi, the pathogenic fungi, grow in very acidic and very oxidized condition. The virus, at the opposite, they develop in the phloem, which is the elaborate sap with the sugar. The phloem has much lower redox potential and high pH. To load the phloem, you need a high pH. So viruses are adapted to the condition of phloems that are too oxidized. When the plant gets too oxidized, the redox in the phloem raises, and the virus will develop with. And the bacteria, it will depend where they are, but they each have their specific zone, EH, pH, where they will grow. So if you make the plant able to not propose this kind of favorable environment for the pathogens, they will just not be able to develop.
So interesting. Yeah. Excuse me if this is wrong, but is it like a nature show where the wolves are attracted to the elk that are the weakest? You know, that a plant that's the strongest can better defend itself against some of the things that can take it down.
Yeah, basically the plant has more energy to protect herself, and the environment it creates is too reduced for the pathogens, and you will have the same things for insects. It depends of the kind of insect. If they're the insect that are sucking in the phloem, they prefer very different conditions than the ones that are eating all the plants. They don't develop. They don't have the same digestive enzyme, and they don't develop in the same conditions. So clearly, the plants that get sick are the plants that are too oxidized. And the different type of pathogens or pests will depend on the pH also and the electrical conductivity. But basically, we find clear area, and we publish this map of where we have the main ones. And once you look at this with this perspective, where are we on EH pH condition? You understand many things. For instance. Probably many farmers know this book, plant nutrition and mineral nutrition and plant disease. It's a reference book where in one of the article they were comparing the effect of ammonium versus nitrate nutrition of the plant, and what was the impact on something like 40 or 45 diseases. Okay, and there was about half of them where nitrates would increase the disease and ammonium would decrease them. And the other half was the opposite. So you say, wow, you don't understand why. Why nitrates sometimes increase, sometimes decrease. When you look at this and when you observe the kind of pathogen it was, nitrate was increasing the bacteria, the fungi, the aerial fungi, the bacteria, and the virus that grows at higher pH and higher redox. The one that were increased by ammonium nutrition were the soil necrotrophic fungi that will eat all the cell. So they were perfectly in the zone. As I said, you feed the plant with ammonium, you acidify, and you bring to this kind of soil fungi, necrotrophic fungi. You feed the plant with nitrate, you alkalinize, you shift to virus, bacteria, and aerial fungi. So it gives a real perspective to understand things that if you don't have this perspective, you don't understand why are we measuring these things. It's the same thing has the completely different impact on different pathogens. So it's really a light. When you start looking at this way, you look at pH, EH on the diagram and say, I'm here, I will get fungi. I'm here, I will be safe. So that's no.
In your research, did you have a light bulb moment when it all kind of connected, or was it something that you had suspected could be the case, that this area would help getting to the balance, and then you worked your way to it? Was there one signature item that happened that made you realize, yes, this is a fully functional thing for agriculture to benefit from?
There's so many bricks, so many interaction. It really build up slowly, but it's like an image. When you open an image on the internet, it can be moving up, or it can be pixels that are getting clearer and clearer. Here, really, we are with pixels that are getting clearer and clearer, and the picture is getting really coherent and really clear now.
Oh, that's wonderful, and we're going to prosper from that. A few final questions for you. How about foliar nutrition? Does it play a role in potentially getting the best balance?
Yeah, especially for micronutrients. As I said, you can have iron and manganese deficiency that are created by the redox and pH condition in the soil. So they are induced by the chemical condition in the soil. Which are regulated by the physical condition, biological condition, but you have an induced deficiency. So if you bring iron or manganese to the soil, we will not bring iron, but manganese to the soil, or if you bring, you will not solve the problem. This element will get insoluble rapidly in the soil, and then it's still the same problem for the plant. If you apply it directly on the leaves and under a reduced form, because if it's again oxidized, then, and that's an important point. If you can have it under a reduced form in your sprayer, but if you spray it with high pressure, with a lot of turbulence, with micro spray, then it gets oxidized.
Mm-hmm. Yeah.
So you have to be careful in foliar spraying, rather large drops, low pressure, so that the nutrients or the microbes also you can spray will stay under reduced and the form, which is the one that the plant can absorb.
Right materials applied correctly. So there's a lot of keys to making this positive. Biostimulants, your thoughts there? How helpful can they be?
So again, there's the different categories. The one for the soil, they can help strongly in creating this, improving the soil structure. For me, I see this as germs of aggregation. You need to bring the microorganism, but also some food. But locally, you will create conditions that will allow them to develop, and that will start this aggregation process. So they will start to improve. I think you bring energy and worker at the same time, and you can build your house properly. Then you have the one that are targeted to the plants. So with different aspects, you can bring them energy directly with very reduced condition, acidic reduced condition. So a lot of energy, so the plant can benefit directly from this energy. But quite often at the same time, you also bring micronutrients, so you will help the plant to have better balance and to have better photosynthesis, so better growth, so collect more energy, and it will be a good start. Yeah, there's plenty of use. We need to work on the soil and on the plant, especially when you are on very degraded soil. You have to work directly on the plant so that they can grow well and feed the microbes that you have in the soil that will do the aggregation.
I'm glad that they can be a positive tool, and there are a lot of biostimulant companies now in the biological arena. I've heard that there are more than 1,000 that are currently active. Do you feel that they have a future as long as the proper research is being done and there is applicability for farmers?
Sure, but there's one key condition: you need to feed them.
Yes.
So, and to feed them, you need the plants. So, if you keep business as usual with monocropping and pesticide and all these things, they will not survive. So they will not do the job, yes, simply. So you really need to have all these things around cover crops, intercropping, increasing the amount of photosynthesis all along the year, increasing the amount of sugar that are the soluble carbon that is released in the root. So if you feed them, they will help you do an excellent job, make this soil structure stable, regulate the redox, because the soil structure has a tremendous impact on redox regulation in the soil. Okay, a good soil structure, you always have some water, some air, so you will have a balanced redox. Especially with a good soil structure, you also have organic matter, which is the reservoir of electrons and protons. So a good soil structure, you will have a diversity of redox and pH condition, but fluctuation in time will be limited. And this is extremely favorable for the microorganism that will help the plant. At the opposite, with a poor soil structure, when it's raining, everything is in under asphyxia, anaerobia. So only the opportunistic bacteria will develop, and they are not favorable for the plant. And as soon as it dries out in 2 days, you are in overoxidation, and then you have only the fungi, most of them pathogenic. So the soil structure is the key for redox regulation in the soil, and the plant does not need to spend energy to regulate redox around the roots when it's balanced naturally in the soil.
Looking to the future, what is your thought a decade or so from now about the adoption of what we discussed today in commercial agriculture?
I hope, I think there's no way out. If we don't
Yeah.
use this properly to regenerate the soil rather rapidly, because with the changes all over the world that we see, if we don't have if we don't use them rapidly but properly, that means together with plants, with cover crops, with they need energy, and all the energy comes from the plants. So we need them to help the plant grow, to make the soil better. But applying them on a bare soil will do nothing. So we need to do this jointly: the cover crops, the intercropping, agroforestry, animal the farming also in the same time, because they bring a lot of other microorganism and reduce component also for all the carbon cycle will be changed. So if we don't do this, we will be in big trouble. I would say. we can do it. That's the good thing. It's possible. It's not too late, but we have to go quite fast. Once the soil will be regenerated all over the world, we won't need them anymore. But I think I will be dead by that time.
Well, so we talked about it's a necessity. There are all the markers there to make this a very successful enterprise for growers. If indeed it is adopted on a widespread fashion, how positive would that be for agriculture, for sustainability, for profitability for growers, for consumers, for healthier produce? The list goes on and on. How, if this is achieved, how positive would it be for our world?
We have the means. When we understood that if we have a good soil structure with a lot of organic matter, with biological activity that we created with by bringing this, we made the process faster by bringing energy in the system. We will have soil that are suppressive of the disease. Okay, that means that the plant will spend most of the energy to grow, and they will be reduced enough. They will have enough energy to make all the secondary metabolite, to make all to produce all this antioxidant, to have bacteria producing the different all the components the plant will need. So we will have no more disease, no more to treat. So that will be that's preventive protection of the crops. We prevent the pathogen to develop, so we don't need to spray any pesticide. So most of the pesticides are strongly oxidizing. We talk a lot about the benefit of antioxidant for health. If we don't press pesticide, we have a benefit on health. If we have more nutritious food, because this plant will have more energy, they will make reserve of energy, and you will have more nutritious food. You will have more antioxidants in the food, so you will have better food for health. So you can also think about the cycle of water, having a large storage capacity with regenerated soil. You will store more water when there's a big storm, instead of the water going down to the river with some soil. You will keep the water there, so you will regulate this cycle of the water. So you will rely less on irrigation if you have it. Many times you don't have it. So all the process, there will be virtuous cycle. You will just raise the productivity. You will lower the cost. You will increase the sustainability. You will increase the resilience. So it's all benefit, in fact.
Oh, that's amazing. So a lot of this is education, getting the word out, but there's still more research to do, of course. What's next for you?
So we have to better understand what are the impact of our practices. What's the impact on oxidation of a plant when we spray an herbicide that is supposed to be selective, for instance? What's the impact on the other side when we spray microorganism, when we spray biostimulant? Does it have an impact really on the plant pH, but also on the nutrients? With the tools developed by Sensin, we can also measure most of the nutrients in the plant. So it will be easier to adjust. So there's really an important step of research to understand where really we want to be for each plant, because it's specific. We have very, very different pH condition according to the crops. Grape wine is, we don't know why, but grape wine, the leaves have a pH around 3. For rice or corn, it will be more 6.5. For tomatoes, potatoes, it will be more 6.5, 7 with a higher redox potential. So each species has its own conditions. So we need to understand what are the balance conditions for each plant. We need to understand, for instance, the impact of the variety on the capacity to regulate this, because the measure we do at a given moment is something, but the most important is the capacity of the plant to keep the balance most of the time, and especially during the night, because during the night there's no photosynthesis, there's respiration, so redox potential goes up, pH goes down, so we have acidification, oxidation, and this is very favorable for many pathogens. So if the plant has the capacity not to go to acidify too much and oxidize too much during the night, it will be resistant. Okay, it's like having a small battery or a big battery. So you can look at the charge of your battery. If it's okay, it's 220 volt for each battery, you say it's the same. But if there's a big one and a small one, it will not be the same. You will not start a truck with a small battery. So that's the key point, the capacity of the plant to sustain the balance and to have this buffering capacity to avoid strong fluctuation. That's one point. And the other point, I think a more fundamental aspect is looking at the interest of all the hydrogen producing bacteria. For me, that's a key to health. That's one of the impacts that is neglected for the legumes, because the nitrogen fixing bacteria, they also produce H2, and H2 will regulate many things. It will reduce. H2 is proton plus electron. So it will provide a lot of energy to the plant, regulates many things. It's like an hormone that we have not paid attention to. So that would be for me fascinating things to work on in the next years. Yeah.
Wonderful. Well, you are fascinating. Your passion is very clear. It's been a lot of progress here, and we're really excited for the future. You were interviewed by John of the Regenerative Agriculture podcast, and he called you a voice of clarity in a wilderness of chaos. And you speak very well, and these principles are so incredibly exciting. Thank you for spending time with me today.
Thank you for the invitation. It was a pleasure.